There we go. Okay, welcome. Monday, October 5, got a class session today. And I've got some notes I want to make with you about the homework I'm reading. It was the homework I'm reading about the ship problem. And then I also sent you an email yesterday with some general suggestions. And I wanted to point out that I will not be here this week in the second session because I'm going to be away at a conference. But the things I show you today will get you through the whole week, and then you can get started on your next homework problem after you hand in the problem tomorrow night. Okay, and if you have a question as we go along, just leave those in the chat window and we'll fill in questions here. So a couple things I want to make notice of, and last couple homeworks in particular. Be very careful when you're doing calculations, multiple calculations on the way to the final answer. So you've got a lot of times small errors that are creeping into your answers when you round off at the intermediate steps. Don't round off anything until the very end of the problem. And that doesn't mean you write down all the digits necessary to do every intermediate calculation. It just means you enter. You can have the calculator hold on to those digits. You enter the exact values you're given in the calculator for the final calculations. So don't round off till the very end of your problem. Okay, next problem. And a lot of people were doing this on the ship problem, looking up something like law of sines, law of cosines. And we haven't done the law of sines or law of cosines yet. So in that ship problem, it was section 2.4, and it was illustrated in section 2.4. You were specifically talking about components of vectors and using right triangles to add together the path of a ship or a plane or a person walking in two different directions. So that is specifically what they wanted you to use on that problem, and they illustrated it, and we illustrated it. If you're going to bring something else to do the problem, and you can do the problem correctly, I don't mind at all, but then you're going to have to explain to me what the law of sines or cosines is. So stick to the technique that he's using in the sections that the problems are coming from, in the sections that we're doing. Here's another thing that, and the reason for that is there's a purpose to practicing and reading the textbook and the sections and the techniques he's presenting. So we will get to fancier stuff later, but you have to be able to, it's not, say this carefully, it's not about getting the right answer, although you want to get the right answer, you need to get the right answer. It's about how you express the answer and how you understand what the answer means. So just to say that the ship is 151 miles from where it started, well, that's true. That's not useful if you can't explain how you use the vector components to get that. And that's what they wanted. Here's another thing that you got to be careful about, but it's showing up when you draw triangles. Sometimes you guys are drawing triangles, just generic triangles, and then saying, oh, opposite over hypotenuse, that's sine. Opposite over adjacent, that's tangent. But that's not true if you're not talking about a right triangle. So make sure that if you're using this idea of opposite side over hypotenuse or opposite side over adjacent, that you're talking about a right triangle, or else it's not valid. I could draw a picture right here. Here's a very rough picture. Let's say that this 45-degree angle, so one box over, one box up consistently. Let's say this is 4 boxes on the short side here, and the long box is about I don't know, I just picked a number like 6.4, you know, something that's like 4 plus half of 4 again. Now, there's no way you can say the tangent of 45 degrees is opposite over adjacent, because this is not a right triangle. You know the tangent of 45 degrees has to be 1, because you know that in a right triangle that has angles of 45, 45, and 90, the two legs of that triangle have to have equal length, whether they're 1 or 10 or 2.5. Those two legs have to have equal length. And there, the opposite side over the adjacent side will always have a ratio of 1 to 1. Sorry, drawing too much. So are we having class Wednesday? No, in the email that we sent out yesterday, what we said is have class today, office hours today and tomorrow, but no class session on Wednesday. Okay, good question. So yeah, make sure you're checking any emails we send out too. Okay, so do not say sine, cosine, tangent, secant, and use sides opposite, adjacent, or hypotenuse unless you're physically talking about a right triangle. You can't say the sine of theta is opposite or hypotenuse if you do not have a right triangle. So I'm reading that homework. I'll finish up reading it today sometime and put it back in your folders that I return papers to you with a grade report. But those are the things I noticed recently so far. Okay. Let me just number this so we can post it later. Okay, very good. Are there any other questions? We just talked last time about arc length and area of a sector of a circle. And I'm going to show you one more example of that today. In particular, the value of measuring things in radians. So today we'll show you new things that say radians is the way you want to measure an angle if you're doing calculations about angles changing with time, or if you'd like to draw a certain representation of how the angle changes with time. Okay, let me get I wanted to reach over the shelf and get my can lid so I can make another circle drawing. So that's where we'll get started. Okay. So make a rough drawing of this circle. I can't remember where I put the card I was using to measure its radius. So I'm going to have to pull out a new card here. So let me try to mark this circle carefully. And let's say without bending the card, maybe bending it was too hard. Let me make a card mark that's give me the radius of that circle. And then I'm going to take that mark and transfer it all around the circle like we did previously. I'll just try to take a second to make this as neat as I can. Okay. And let's draw this angle. Okay, so remembering what a radian is. A radian is the angle you get if you take a circle of radius r and walk a distance r on the outside of that circle. This is the distance r, and this is the radius r. And to distinguish between the two of those, when we walk on the outside of a circle, that's called an arc. So the arc length, or distance that you walk on the circle, make that equal to r. Now, exactly how many degrees is a radian? Well, we have a method of converting, but I want to say to you, it's got to be nearly 60 degrees, because let's pretend I join these 2 points on the circle where I start and stop the angle. If that red arc is r units long, meters, feet, inches, whatever units I'm using, then this blue distance here has got to be slightly less than r. Almost as if I took an equilateral triangle with 3 equal sides, r, and r, and then we said last time kind of bent or pushed out this side like it was flexible, like it was a straw. If all 3 sides of the triangle were r, then we know the angles would all 3 be 60 degrees. So I've got to have pinched this triangle a little bit. So as far as degrees goes, what is exactly 1 radian? In degrees? Well, we'll go to our conversion formula. If I want to convert degrees to radians, we told you that you multiply by pi over 180. And pi is that unusual number, 3.14159. Very close to 3, but not exactly 3. And if I want to create radians, if I want to take a radian, find out how many degrees it is, I'm going to do the opposite. I'll divide by pi over 180. Or you could say I'll multiply by 180 over pi. And that'll tell me how many degrees I have. So if I want to know what 1 radian was in degrees, then I just say 1 radian times pi over 180. Then I ask my calculator what pi times, what 180 divided by pi is. Pull out one of the calculators here and say, well, really, 1 times 180 over pi is just 180 divided by pi. Pi is a little bit more than 3. 180 divided by 3 would be 60. That's if all 3 sides were equal. So divide by a little bit more than 3 should be a little bit less than 60. And it happens to be 57 point, let's call it to the nearest 10th, 0.3 degrees. So you don't have to use that often, but if you're just trying to eyeball what 1 radian is, it'd be about 57.3 degrees. It's usually more convenient to talk about radians as in fractions of pi, which is how we divided up the circle before. 15 degrees is how many radians? Multiplied by pi over 180 And because 15 goes in evenly to 180, it goes in 12 times, then 15 degrees is pi over 12 radians. How do you see pi over 12 radians on a circle? Well, remember, the whole walk around the circle is arc length 2 pi r. We're using this formula for arc length. Radius times angle. The whole walk around the circle is 2 pi r. If theta is 2 pi, the arc length or the arc walk or the arc distance is 2 pi r. So halfway around the circle would be pi times r, walk. So that means the angle here would be called pi. 0, 2 pi, and then we labeled these other sides last time as well. Pi over 2. This angle we'll call 3 pi over 2. You could visualize pi over 12 as being 1/12 of the way to pi. This is 1/2 of the way to pi. This is 1/4 of the way to pi, 45 degrees. 1/12 would be 1/3 of 1/4. That's the 15 degrees. So pi over 12 would be 15 degrees, or 1/12 of the way to pi. Okay, but what I want you to be ready for or used to is, how do you visualize? Not if someone gives you a fraction of pi, but what if someone just gives you a raw number like 3.7 radians? Exactly how many degrees is 3.7 radians? Well, I could estimate it on the circle, then I can calculate it with a calculator. This is 1 radian, about 57 degrees, 2 radians, which would be about 114.6 degrees, 3 radians. I could literally multiply 57.3 by 3. But 3.7 radians, I'm not so fast at. I'm going to let the calculator handle it. This is 4 radians. 1, 2, 3, 4 radians. 3.7, if I'm eyeballing it, must be somewhere in there. Let me pull out another color. Let's call 3.7 about there. So here's 3.7 radians. But if I want to know exactly how many degrees that is, I'm going to use my conversion formula. 3.7 radians times 180 over pi is going to give me the number of degrees I have. So don't think that anytime someone gives you radians, they must include a pi, like pi over 12. You can just have an ordinary number that represents walking around the circle. I'm going to check this on the calculator. Just say 3.7, enter it just like that. Sorry. Clear 3.7 times 180 divided by pi. 211 degrees, nearly 212 degrees. Very nearly 212 degrees. That looks credible because I know halfway around the circle is 180 degrees. So this could be 32 degrees past 180. That doesn't look like a 30-degree angle there, but maybe I didn't draw my 3.7 nicely. But at least it's possible, it's credible that that represents approximately 212 degrees. Okay. Likewise, if someone gives you a certain number of degrees that's not even, like what should 80 degrees be in radians? Now 80 degrees is nearly 90 right here. So it's up here, right? About 10 degrees away from 90. If this is 80 degrees. What does it look like on my little radian wheel here? Here's 1 radian, here's 2 radians. Is it about 1.5? It's halfway, it's a little bit less than halfway. Is it about 1.4 radians? Let's say we estimate it to be 1.4 radians. But we can know the exact value. Multiply that by pi over 180. I can even simplify. 80 goes into 180. How many times? You know, I can cancel a 2, 40 over 90, cancel a 10, 4 over 9. I mean, I can name it with a fraction of pi, 4 pi over 9. But how many radians is 4 pi over 9? I'm going to have to multiply 4 times pi and divide by 9. 4 times pi be a little bit more than 12. 12 divided by 9 would be a little bit more than 4/3. 4/3 about 1.3. Let's do the actual calculation. 4 times pi divided by 9. 1.396. Now, if I round that off to the nearest hundredth, it is 1.4. So our estimate up here of about 1.4 radians, 1 4/10 of a radian, is reasonable. Don't hesitate to make a drawing of the circle and to measure things against that drawing, at least just to eyeball it, just so you have some feeling about where things are. Okay, so now let me show you something else you can do with this formula. Second piece of paper. So this is arc length formula. S equals R theta. This is the arc length. This is the radius of the circle you're walking on. And this is the angle of the circle that you've traced out, but always in radians. You know other terms that deal with circles and moving on circles, but not just walking, but maybe how fast the circle is spinning. So let's talk about a wheel that's rotating. Something that's rotating so many times per minute, or rotations per minute. Sometimes people call those RPMs. Rotations per minute in an engine. Rotations per minute when you're riding a bicycle. And one rotation is literally 360 degrees. So if you're going through one rotation per minute, you're going through 360 degrees per minute. And I mention that because the second hand on your watch has to go through 360 degrees in 1 minute. I got an old broken watch sitting next to my desk. I mean, it's broken that the band is broken, but it was still a reasonable watch in its day. So there's a second hand moving, and you can watch and count how long it takes to go 360 degrees. But that's not going to surprise you that it takes 1 minute to go 360 degrees. That's what a second hand does. It measures out 1 minute in one full circle. So second hand goes 1 RPM, 1 revolution per minute, 360 degrees in a minute. Of course, 360 degrees is 2 pi radians. So you could say that the second hand moves 2 pi radians per minute. So the second hand on your watch has moving 360 degrees per minute, or 2 pi radians per minute. That's a measure of the speed that the second hand is moving. It tells you how fast it's moving, but it's not moving in a straight line like you and I would run. That would be called linear speed or linear velocity. Linear velocity is the amount of distance you cover in a certain amount of time, not the angle you cover the distance. If you're doing a 100-yard dash, well, the best people in the world, when they do a 100-yard dash, they're certainly under 10 seconds, right? And I can't remember because I haven't seen the Summer Olympics because they didn't happen. But if I was the top of my head, best 100-yard dash, and you guys could look it up, or I could look it up, but it's probably somewhere around 9.5 seconds. And they don't even call it the 100-yard dash, right? It's the 100-meter dash, which, since a meter is slightly more than a yard, 100 meters is slightly more than 100 yards. Okay, but if I say I ran 100 meters in 9.5 seconds, that'd be a measure of my linear speed or my linear velocity. Now the question is, can you relate these two things? What should you call it when you measure angles per unit time? That's called angular velocity. RPMs is an example of angular velocity. 4,000 RPMs means that object is rotating 4,000 times in 1 minute. The second hand rotates 1 time in 1 minute. Now you can relate that to linear velocity in a kind of a simple way if you think about what arc length means. So let me take length right here, and let me take angle right here. And if I divide length by time, I get linear speed. That's what you and I ordinarily call speed. 100 miles in 2 hours. That means I was driving 50 miles per hour. That's what you and I generally call linear speed. But how does the car tire deal with that? How many rotations does your car tire go in that number of miles? If you divide this side by t, then you'll find out the angle you turned in t seconds or t hours or t minutes. And if the wheel's turning pretty fast, then in a minute or in an hour, you're going to make many, many rotations of that wheel. This is called speed, but it's the speed of the changing of the angle, called angular speed. Let me give you an example from a problem in the book. So, and I'll put this under my camera before I write it on the paper. So you're going to explore the problems in 3.5. But this is 3.5, just an example, problem number 49. I should pull it up on my screen. That's true. I'll make it more readable under the camera. Let me put a book under it. Let's just read it here, and I can refer back to it later. So a woman's riding a bicycle for 1 hour. She travels 16 kilometers. Find the angular velocity of the wheel. How fast is the wheel rotating if the radius is 30 centimeters? Okay, let me draw a rough diagram of this. So I am not drawing this to scale, but let's say this distance right here is the distance the woman rode the bike, which was 16 kilometers. That is, a kilometer is 1,000 meters. So it's 16,000 meters. And she did that in 1 hour. So her linear speed, and we use the letter V for linear speed. V is a traditional letter used for speed. Her linear speed was 16 kilometers per hour. We usually abbreviate kph, kilometers per hour, or you could just write it out completely. 16 kilometers in 1 hour. You can imagine the bicycle wheel rotated many, many times in that hour. And the bicycle wheel was exactly, go back to the problem, 30 centimeters. Now, let me draw a bicycle wheel here, but no way is that bicycle wheel that large compared to 16 kilometers. This drawing is not to scale. I just want to help you visualize this. So let's say that that bicycle wheel has a radius of 30 centimeters. Now I got to compare kilometers and centimeters. Kilometers, very large. Centimeters, relatively small. Let's talk about centimeters. A centimeter is 1/100th of a meter. So if I want to express this in meters, this is 30 parts per 100, or 0.30 meters. Not even half a meter. So this distance, 16,000 meters. This radius of this bike tire, 0.3 meters. How many times did that bike tire rotate in 16 kilometers? So I could calculate that just by saying, how many rotations did the bike tire make? Be 16,000 meters divided by 0.30 meters. Now that's going to be rotations, not degrees, not radians. One rotation is 360 degrees. One rotation is 2 pi radians. So let me take 16,000 here and divide by 0.3. Sorry, 0.30. This tire rotated 53,333 times and some change. But let me just say it rotated about 53,333 times. There's the exact number. There's a threes going on forever. That was rotations. And it happened in 1 hour. Now I'm going to think about this. How fast was she going in plain English? And I could think about, how fast I ride a bicycle, how fast you ride a bicycle. But 53,000 rotations in 1 hour sounds like a lot. Rotations per hour, that's not a standard abbreviation. Let's say how many rotations per minute that would be. Let's divide 53,000 by 60. 889 approximately RPMs. Her bike tire was rotating at 889 RPMs. Now let's think about that in rotations per second. How fast was she pedaling? Let's divide by 60. 14.8 rotations per second. That sounds like a lot. I'm thinking of me riding a bicycle, and I'm thinking of that bicycle moving. It may not be impossible, but rotations per second, nearly 15 rotations per second. You know, you count 1,000. 30 centimeters, and we got to convert this to, well, sometimes it's easier to think in inches, but 30 centimeters is a relatively large wheel. Typical bicycle wheel maybe about 27-inch diameter, 28-inch diameter, fancier wheel. And each inch is about 2.5 centimeters. So 28 inches, about 15 inches radius, 14 inches radius, times 2.5 would be, this is not a full-size bike. So a full-size bike, if I took 14-inch, 13-inch radius times 2.5, I'd be getting about 33 centimeters. So he might have just been approximating the size of that bike. Now 16 kilometers per hour is what in miles per hour? There's a silly way you can change kilometers per hour to miles per hour. Every time you ride 5 miles, then you ride 8 kilometers. That's something you can check on speedometer, perhaps. So if you want to change kilometers per hour to miles per hour, then you can multiply by 5/8. Let's say 16 times 5/8. She is not going super fast. About 10 miles per hour. So that would be a leisurely pace. I mean, if you see some people shooting by on their fancy bikes, they're going about 20 miles an hour. If you're talking about Tour de France, which must be over or nearly over, I saw some of the early stages, they're doing 30 miles an hour, going downhill, much better than that, 40, 50 miles an hour. That doesn't sound too impressive. Say they're doing 30 miles an hour and then some person you see out on the trails doing 20 miles per hour, right? But the guys in the Tour de France are doing 30 miles an hour for 80 or 90 miles. So they're in a particular shape. Okay, so what we want you to do is to be able to, people use this funny W. It's kind of a wavy W. Greek letter, it's called omega. This is the letter people use for angular velocity. How many angles are you going through in a certain time? So now you have a formula on your formula sheet that talks to you about arc length for a given angle. And now you have a formula that talks to you about speed for a given rotation. These two formulas go together. This is arc length. This is speed. This is angle. This is angular velocity. Angular velocity is defined to be the amount of angle you go through in any unit time. Just remember, when you're doing this calculation, you always measure the R in radian. So this is another example of why you want to use radians to do these calculations. Okay. Try some of the examples in 3.5 and tell me what you think about that. But I want to turn the corner now into chapter 4. So we've talked about sine, cosine, tangent, secant, cosecant, cotangent. We've talked about how to use them, but I really haven't thought about drawing them in their own right. Think about that. You've only drawn triangles. You've only thought of sine and cosine as ratios of the sides of a triangle. Hypotenuse, opposite, and adjacent. You can spit out a lot of values, like, oh, the sine of 45 degrees. That's 1 over root 2, because I know that famous triangle. The cosine of 15 degrees. Oh, that's root 6 plus root 2 over 4, because I know that famous triangle. You can convert any one of these numbers to an approximation by asking your calculator, if you're in degree mode, what the cosine of 15 degrees or the sine of 45 degrees is. First, sine 45, just as an example. Approximately 0.7071. Cosine of 50 degrees, approximately 0.9659. And you can do many other angles besides. But what would happen if someone asked you to graph sine or cosine? Then they're asking you for a particular drawing. If someone says to graph sine of t for t from 0 to 10 seconds, or from t just from 0 to 10, whatever units you're using to measure, they're asking you how t changes, how sine changes as this t changes. I can write down a lot of famous points, like the sine of 0 is 0. The sine of pi over 2, 90 degrees is 1. The sine of pi, 180 degrees is 0. The sine of 2 pi, I'll stop off at 3 pi over 2 first. Minus 1. The sine of 2 pi is back to where I started, 0. But those are only individual points. 0 radians. That's just strictly equal to 0. Pi over 2 radians is about 1.57. Pi is about 3.14. 3 pi over 2 is 1.5 pi. It's about 4.73 if you added those two numbers. 4.71. 2 pi, it's about 6.28. So what would happen if I used my knowledge of sine or cosine and tried to draw it over a certain time period? And let's say from 0 to 10, 2, 4, 6, 8, 10. I know that sine is going to keep repeating. And I'm not comfortable with these decimal approximations, right? I don't think I should use these decimal approximations, but they're fair. At 0, the sine is 0. At 1.57, sine is 1. Where's 1.57? It's about right there. If I call this 1. At 3.14, the sine is back to 0. It's a little more than 3. Oh, okay, sorry. I made my dot in the wrong place. This is 2, 4, 6, 8, 10. So 1.57 is about here. 3.14 is about here. 3 pi over 2 minus 1 is about 4.71. It's about right here. And 6.28 is a little bit past 6. It's about right there. Look at the changes that sine went through in that short time. It rose to 1. It could be no higher than 1, and it started falling. It can go no lower than minus 1 because of the ratio of the sides. The opposite side will never be larger than the hypotenuse. And then it climbed again back to 0. After I reach 2 pi, I know that I'm going to go around the circle again, and I'm going to read the exact same sine values. So if I add another 1.57, I'll be back to 1. That's a little bit awkward, but let's say 7.85, I'll be back at 1. If I add another 3.14 to 6.28, that's 9.52, 9.42, I'll be nearly at 10, and I'll be back to 0. Sine graph looks something like this. It rises and falls between 1 and 0. And it repeats itself endlessly. Before I reach 10, now remember I'm about 9.4 something right now, I guess it would start falling again. So if I drew a picture of this on a calculator or on a computer, and someone said, what does sine look like for the first 10 seconds of its life? I should get 2 high points, 1 low point. I should get 1, 2, 3, 4 points where it's on the axis, where it has height 0. And it should end with this little tail below the axis at about 10. I haven't pulled out the calculator lots of times for graphs. I prefer decimals sometimes, but let's try to draw this on the screen of the calculator. Now I'm thinking about radians, right? And so this is really important. Whenever you graph sine, cosine, all the other functions, always think in radians. So I'm going to change this mode to radian mode. And then on this calculator, I must have been doing something else. I'll type in sine of x. The calculator is not super flexible. It just uses x for the input letter. And in another context, it might use t, but I'll just use x. And then for the window, let's run this from 0 to 10. Let's make marks, that's the x scale, every 2 steps. And let's do the y. Remember, it could never go above 1 or below -1. Let's just say safely from -2 to 2. Let's see what that graph looks like. The y scale, let's let the y scale be 1. So 1 mark will mean 1 unit of height. The calculator has other things in here called resolution and other things. Right now, I'm just going to draw the graph. Sometime later, it could tell you what the resolution does. 1 high point, 2 high points, and then by the time it reaches 10, it hadn't quite come back to down and up again. But it was a little bit lower for a split second. Okay, this is traditional graph of sine. Likewise, I could draw the cosine graph here, and I'll explain what it looks like later, but let's add the cosine graph. Excuse me. And this is sometimes handy on your calculator. I draw them both at the same time, and you might forget which is which. But on this calculator, any similar calculator, what I could do is make the line I draw darker. I can make lots of choices, but hit the Enter key, then you make the line darker. Here's the cosine graph. The cosine graph also waves between 1 and -1. In fact, it looks exactly like the sine graph, except that it peaked earlier. It started up at 1 instead of down at 0. Okay, I've gone through a repeating, or at least starting to repeat. Cosine starts at 1, and then it comes back to 1. Sine starts at 0, and then it comes back to 0 and restarts. When we talk about that restarting, that's called the length of the period of the sine or cosine. How long did it take sine or cosine to restart? Let's take a look at this image right here. Well, it restarted when I went back to 0. Not back to 0 like coming down from the high point, but executing high point, executing low point, and ready to execute again. It started over at 2 pi. And the fancy word for that in mathematics is period. The period of sine or cosine, the natural period, is 2 pi. We could change that period, but if you just give a straight up sine t, cosine t, sine of x, cosine x, it's going to repeat itself after 2 pi steps, after 6.28 steps on this marker. But you know what I want to do is I want to stop thinking in decimals. And again, this is the utility of thinking in radians, right? So let's not mark this horizontal axis in the counting numbers that we're used to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's mark that horizontal axis in fractions of pi. I can always convert a fraction of pi, like 1.5 pi's is 4.71. But I don't like the imprecision of dealing in decimals. Let's draw a nice large picture of sine where I mark the horizontal axis in fractions of pi. And I'm going to make this picture fairly large, just so I can draw more details on it. Let's call this 1 unit, 4 boxes. Let's call this -1 unit. Those are key points because I know that sine and cosine never are bigger than 1 or less than -1, right? Then let's mark out equal spaces here and call it pi, half pi, 2 pi. Now, I don't know where to mark them per se because it's not going to match the 1. 1 is a different unit than pi. But let's call this pi over 2, 1 pi. Now, I am not saying like, oh, pi is a little bit more than 3, so I'll make it 6 boxes exactly. No, I'm just measuring something casually equal. Pi over 2 pi. Let's make every 3 boxes worth a half a pi. This would be 3 pi over 2. Another 3 boxes would be a full 2 pi's. Half pi, 2 halves pi, 3 halves pi, 4 halves pi. Let's try it again. Another half pi, full pi would put me at 3 pi. And another half pi and full pi would put me at 4 pi. Now notice that's enough for 2 cycles, 2 periods of sine or cosine. 1 period is 2 pi units. I don't like the way I marked that off. I'm trying to say, wow, does that look equal? It's because I have this line not in a nice place. Here's 1 period, 2 pi units. Let's mark all those points that I had a second ago. Think like this when you want to draw a sine, and let's just draw 1 period. It starts dead center at 0. Then in the middle of the period, it's back to 0. And then at the end of the period, it's back to 0. So starts at 0, 1 period, it comes back to 0. And in the middle, it's also 0. Think of these like stars in a constellation, like the 3 stars in Orion's belt. At pi over 2, the sine was 1. That's as high as it ever gets, and that's halfway between 0 and pi. And here, I mark that conveniently on the scale. 3 pi over 2, the sine was 0. Think of these 5 dots as a constellation. When you see the stars in the sky arranged in a certain pattern, then you say, oh, that's the Big Dipper, that's the Little Dipper, that's Orion, the hunter. Orion, the hunter, I don't know exactly what it looks like, but I know it's got 3 bright stars at its middle belt. I could find other points where I measure sine and cosine. For example, the sine of pi over 4, remember, pi over 4 is 45 degrees. Sine of pi over 4 is 1 over root 2, which is about 0.707. I could mark pi over 4 if I wanted to, and make it about 0.707 high, maybe about right in here. Now that's just eyeballing it. And at 3 pi over 4, it comes back down at the same height. This, let's make it smooth, not too pointy, flat at the top. I want to make a nice sine drawing. This is 1 bump of the sine graph. Sometimes people call that 1 node or 1 nodule of sine graph. What happens is I visualize going around the circle and then going around the circle on the underside. Well, the sine is the height, the y coordinate. As I go around the circle on the other side, I'll go through the same y coordinates, just upside down. So if I take this bump and turn it upside down, even that 0.7 and 0.7-ish numbers I had, and then gently sketch a smooth curve through that. Now I've drawn 1 period of sine. I could draw another period of sine just by repeating those dots. Starts middle, ends middle, 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 and then middle between those two, let's make that the high point. Middle between those two, let's make that the low point. And you can add more dots if you want to. I'm just going to gently sketch. Don't make it a triangle. Don't make it like triangular like that. Make it a gentle round hill. Now remember, when we drew it up to 10, we got this far after 10. Now, that means 10 must be a little more than 3 pi, because that's the same distance right there. And 3 pi is about, what, 9.52-ish? You can multiply in your calculator. That's right, it's almost 10. This is the same drawing I just drew a second ago, it's just at a larger scale. This is how you want to draw your drawings. Mark every mark that you want to represent on the horizontal axis. Label the horizontal axis, T or X, whatever variable you're using. Mark the vertical axis. Mark the scale and name the scale. Name the scale marks you draw. You don't have to name all the scale marks. Like I could add the other names in here, 5 pi over 2, 7 pi over 2. What is 7 pi over 2? 3.5 pi. I might add other marks, but I don't have to name all of them because that would get very busy. But make your scale consistent. Make each of those marks equally spaced and label enough marks that someone can see what you're drawing. And in a sense, what I reproduced right now is this picture from the book for the graph of sine of X or sine of T. Okay, I could do the same thing for cosine T. So right now, let me draw this so we can keep them straight. This graph in red is the graph y equals sine T. And cosine will go through exactly the same points. Do you remember this statement that cosine is called the complementary sign? So the cosine of 90 minus theta is always equal to the cosine, or sorry, the sine of theta, degrees. Here I'm measuring in degrees. Or I could say it in radians. Cosine of pi over 2 minus theta is always equal to the sine of theta. Well, remember, cosine was also what we talked about last week. An even function or an odd function. Cosine is what? The cosine of theta is always equal to the cosine of minus theta. And we call that even function or odd function. We call that an even function. So I could take the theta and multiply by -1, and I'd still get the same cosine that I started with. I can rewrite this as cosine of theta minus pi over 2 is the same as sine of theta. What does that mean for a picture? It means that the values of the cosine are going to be the same as the values of the sine, except they will occur 1 pi over 2 earlier than they occurred for sine. In other words, the sine of 90 degrees or the sine of pi over 2 will be the same as the cosine of pi over 2 minus pi over 2, or the cosine of 0. And in a sense, it's called shifting. If I want to know the cosine of 0, I could just look at the sine of pi over 2. The sine of pi over 2 is 1, so the cosine of 0 is 1. Same value, it just happened pi over 2 units earlier. I could take every red dot and turn it into a blue dot that's pi over 2 units earlier. I just shift every red dot over. And I'm back to where I started. Let's draw one cosine graph. This looks like what we saw on the calculator screen. You'd be forgiven in a sense if you called it a sine graph. Well, it has the same shape as a sine graph, but it's not starting at the same place. If you trace it backwards, it must start over here at minus pi over 2. You could ask your calculator, the cosine of minus pi over 2 is 0. It's the same shape as a sine graph, but it's literally been shifted. Pi over 2 units left. So how do I think about the cosine graph just for one period, 2 pi units? I think it starts high, it ends high, in the middle it's low. And in the middle of the middles, the middle, it's 0 both ways, going down through the axis, going up through the axis. So I could repeat that. Starts high, at 4 pi it ends high. Halfway between 2 pi and 4 pi, it's a low value of minus 1. Halfway between high and low, it's 0. Halfway between low and high, it's 0. And I can use that to sketch another graph of a period of cosine. That is a neat graph. It's a relatively neat graph. A machine would do better, but if you're careful, you can draw a very neat graph. This graph would be y equals cosine of t. So our mission for the next 2 weeks is not just sines and cosines. Our mission is to draw all 6 functions. Get rid of this window right here. Excuse me. Got that out of my way. Okay, thank you. We want to see in a visual way how the sines and cosines repeat every time I drive around the circle. And for that, let me show you something I put on the webpage. Several helpful things. Let me share this webpage with you. Got it. We're in week 6. We're talking about the basic graphs of sine and cosine, but down here in the technology and handouts. First of all, in the handouts, I mentioned in the email to you yesterday, I've got pictures of all the 6 functions. Let me open up a couple of tabs here. And I've got instructions for drawing them one period at a time, like what we just did for sine and cosine. Here's instructions for drawing sine and cosine one period at a time. You think of each wave, you call this a period or a wave of sine or cosine. You think of each wave as being inside a box that's 2 pi units long and 2 units high, plus or minus 1. And then you can do all sorts of things to the box. You can make the box taller by multiplying by 2, and the box would be plus or minus 2 units. You can make the box thinner by dividing by 2, and then the box would just be from 0 to pi. But the sine shape and these key 5 points always stay in the same position. If you kind of want to say it to yourself as a poem, then what do you have for these first 3 points, beginning, middle, and end? Middle, middle, middle. Those 3 points are in the middle of the box. The left side, middle, the right side, middle, the middle, middle. But in between the 2 middles, between these 2 middles, you have the middle high point and the middle low point. Now, that's not much of a poem, and it's not much of a mathematical description, but that's how I say it to myself when I graph sine. Middle, 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 middle high, middle low. Let's look at one sine wave. Just one wave. Starts high, ends high. In the middle, it's low. And in the middle between the high and the low, it's in the middle itself. So I say it to myself whenever I graph a cosine. Starts high, ends high, middle low, middle, 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 middle. I am not saying that that's the way you have to speak or remember a sine or cosine graph. I'm just saying that that helps me. What would happen if you did something to the sine like scaled it? Let's multiply sine in this picture. Compare these two pictures side by side. Here's a natural sine graph, and then here's a sine graph that's been multiplied by 2, then multiplied by -1, and then inside, I've accelerated the x by multiplying by 3. That means it's going to reach its period 3 times as fast as it normally would. So here's a typical sine graph, but it's upside down. That represents the minus sign. It's been vertically stretched to -2 to 2. That represents the scaling of 2. And it's been horizontally compressed. It took the natural period and divided by 3. So now its period is sine of 2 pi over 3. Another way to say this is that if I put a 3 in front of the x there, I will get 3 waves in 2 pi seconds. Let's try it on a calculator. Let's create a window where I only go 2 pi seconds. You can literally type 2 pi into your calculator, and the calculator will make that the maximum x. Let's make the x scale. You can even make the marks of the calculator at pi. I liked marks at pi over 2 here. Let's make the marks of the x scale pi over 2. Let's make the y min and y max -3 to 3. But let's leave the y scale at 1. And let's just draw a sine graph. Eliminate the cosine graph. What do I see? One wave in 2 pi seconds, and it was height plus -1. That maximum height is called the amplitude of the curve. Sorry, I have to go back to the calculator, stop sharing the screen. Now let's multiply the sine wave by 2. Let's stretch it vertically. The fancy word is scaling. But if I scale by 2, then I've done what? Made it twice as tall as it used to be. Same sine wave, just like pulled, stretched, scaled by a factor of 2. That means a 1 became 2. That means a -1 became -2. And every other point in between. What would happen if I made this -2 here? Well, then I would not only be stretching it by 2 units, but I would be multiplying every y value by -1. I would be turning it upside down. There's my normal sine graph, amplitude 1. Here's the upside down sine graph, amplitude 2. Don't say the amplitude is -2. The amplitude is the maximum height of the sine or cosine graph. So we call that amplitude 2. You could literally take the absolute value of the number in front of the sine or cosine. Now let me do one more thing to match the paper I showed you. Let's multiply the inside here by 3. And when I put 3x in there, what happens is I will get 3 waves in 2 pi seconds. Let me get rid of the minus sign, just so that the upside downness doesn't distract you. Let me get rid of the 2, so the 2 doesn't distract you. Here's a sine wave, natural period 2 pi, and here's a sine wave whose natural period will be 1/3 of 2 pi, 2 pi over 3. There'll be 3 waves in 2 pi seconds. Here comes the natural sine wave. And here comes the other sine wave, much faster. 2, 3. It completed 3 full cycles in 2 pi seconds. On the paper I showed you, I was giving you to practice drawing. Let me go back to the website and share that paper with you. I just didn't display 3 cycles. I just displayed 1 cycle, 1 period as being 2 pi over 3. So I'm thinking of this as my guide box for drawing y equals minus 2 sine 3x. I think of this as my guide box for drawing sine. And in sections 4.1 and 4.2 this week, I want you to practice drawing these and practice playing with the amplitude and period. Now here's pictures of sine and cosine. And then later we'll do tangent, secant, cosecant. These are pictures of all 6 functions. But you can draw all 6 functions just by looking at these guide boxes. I'm not going to start off with secant and cosecant exactly yet, but they just follow the guide box. Secant follows the guide box for cosine. Cosecant follows the guide box for sine. Tangent is its own animal, and I'm having trouble loading that right now. Tangent is its own animal because it's sine divided by cosine. So tangent shape is entirely different. You can use the sine and cosine guide box, but it's got little arms that extend up forever or down forever based on the values of sine or cosine that I have dotted here. So if you learn the values of those key dots, starts, this is tangent, starts middle, 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 but then in between the 2 zeros, it's got an undefined place where this cosine is equal to 0. Or when the cosine is equal to 0 here, 3 pi over 2 or pi over 2. And then in between that first middle and that undefined, I reach the value 1, because at that point, pi over 4 sine and cosine are equal to 1. So check out these handouts to help you start drawing sine or cosine by using this framing box. But if you want to see this in action, it's the last thing we'll look at. I also made a nice Desmos sheet here. So you could see the sine and cosine. Excuse me, I must not have clicked on it. There we go. You can see the sine or cosine as you travel around the circle. Let me blow this up a little bit. It doesn't always resize on your screen unless you want like full screen or something. Let me visualize this. Just want to shrink this a little bit. Nope, not that way. Okay, now I'm just destroying my graph. Okay, let's start out simple. Here's a circle, and you know that on a unit circle, the sine is the y-coordinate and the cosine is the x-coordinate. So the first point on a unit circle has x-coordinate 1, that's the red dot up here, and y-coordinate 0, that's the blue dot at the center. And now watch what happens as I drag that angle around to pi over 2. Well, pi over 2, now sine is 1, because sine is the vertical part, and cosine is 0 because cosine is the horizontal part. As I drag that angle, here's pi. Sine of pi is 0, but cosine of pi is minus 1. I'm going through a full cycle of sine or cosine back to where I started. Back to where I started when sine was 1 at 2 pi and cosine was 0. Sometimes it helps people to visualize sine and cosine like this, is tied to this circle machine. These are the x and y coordinates. Right here, the x coordinate is a small negative number. So this graph goes down a small negative ways. But the y coordinate is a large negative number, nearly minus 1. So here's the y coordinate in blue, large negative number nearly -1. Sometimes it helps to see that happening. Now you don't have to drag this with your finger over and over again. You can just run it like an animation. This is a nice feature of Desmos if you want to see stuff. Right now the animation is going back and forth. I don't know if that's good or distracting. You can change how the animation goes by clicking on those bars. You can make the animation only go one direction. I think that makes it go one direction and start over. You can make the animation only play once and stop, or you can make the animation play continuously. You can speed up the animation. Okay, now like that's going crazy, or that's too crazy, or you could slow it down. Now I've gone many, many times around the circle, so the points are way, way out to the right. They're not near me anymore. And I think I've kind of broken this. So let's put it back to 1 unit speed. Let's put it back to going back and forth. And oops, I just distributed something there. Okay. Notice how it's going from -10 to 10. If I change that 0 to 2 pi, then it wouldn't go off the screen. It would just go back and forth in 0 to 2 pi. I want you to know this shape intimately. I mean, this is a sine and cosine shape, very, very important. So in your homework for next week, I'm going to have you draw these very, very nicely by hand. I don't mind if you have a calculator or computer to help you draw things, but make sure you can draw a sine and cosine very nicely, at least reasonably as nicely as I drew by hand yourself. You can use a calculator to check your work. But this week, you're going to be experimenting with changing the amplitude and changing the period. Let me go away from this figure. Let me go back to my website. I'm going to stop this thing from spinning. So there's a visualization of what sine and cosine mean, like in motion. Okay. I cut one of the sections out of this week just so you could work on 4.1 and 4.2 by yourself for the rest of the week. I'll come back and do more graphs with you, but I'm not going to be available on Wednesday. So I will let you work on section 4.1 and 4.2 by yourself. And then we'll come back next Monday before you hand in a graph of them. And we'll do some more practice with you. And this week, your written homework, if I remember it correctly, was about what? So last week was the ships. This week was the arc of a circle. So what did we do with the arc of a circle? Let me get, oops, I've lost my screen here. My apologies. Let me get this up on my screen again. You're handing in this third one. Oh, sorry. You're handing in this fourth one. Oh, it was the thing we did estimating with your thumb, using the thumb as an estimate for the distance of things. So that's kind of useful. We did an example of that last time. Let me show you the sheet just so you remember it. So if you have a basketball, which is 9.5 inches high, and it's so far away from you that it covers one width of your thumb at arm's length, you can tell actually how far that basketball is away from you. Same thing with any figure, cell tower, a person, or on the bottom of the screen, a car. So you complete this for your homework submission tomorrow night, and then I'll post a new homework with drawing sine or cosine. Okay, I will see you again in 1 week. You can send me email while you're working inside the system, or just email to me directly and I'll answer those in the evening when I'm finished with the meetings I'm at. I'll see you guys in 1 week from today. Have a nice week.